Hey everyone, welcome back to The Explainer. Today we're tackling a really fascinating puzzle. Lesson 5, Simultaneous Linear Equations. You know, if you've ever stared down a math problem with an x and a y totally tangled up together and just felt, well, a little overwhelmed, you're in exactly the right place. We're going to completely demystify this whole process today.
Okay, really quick, here's our roadmap for today. We're going to hit the one unknown goal, Tool 1, which is substitution, Tool 2, which is elimination, then we'll level up with equation scaling, and finally, we'll wrap up with some real-world business applications. Let's get into it.
Section 1. The one unknown goal.
Now, before we even look at a single number or variable, I want to really highlight this core mantra. Our source material puts it perfectly. Every simultaneous equation problem ends as a Lesson 3 problem. The only new skill is getting there. Basically, solving for a single unknown variable is something you already know how to do, right? So our single overarching goal today is just to take a messy 2 unknown problem and collapse it into a really simple 1 unknown problem. Honestly, that's the entire game.
But wait, what does the word simultaneous actually mean here? Well, it literally means operating at the exact same time. In algebra, that means whatever solution we find, whatever numbers we eventually discover for x and y, they absolutely must perfectly satisfy both equations at the exact same time. Not just one. I'm warning you early on, a real solution has to work in both places at once, which, by the way, is exactly why we always check our final answers against both original equations.
All right, let's open up our toolkit. Section 2, Tool 1, Substitution.
This is definitely the most conceptually direct method we have for turning 2 unknowns into 1. Substitution is kind of your natural first choice when one of your equations already has a variable that's super easy to isolate, like an x or a y just sitting there all by itself. So, step 1, you rearrange that equation so the variable is totally alone on one side. Step 2, and honestly, this is where the magic happens. You take that new expression and physically substitute it into the other equation. Boom! You've just eliminated an entire variable. Step 3, you solve that resulting single variable equation. And finally, step 4, you substitute your new answer back in to find the second variable. And of course, check both.
Now hold up a second, because there is a massive trap right here. The biggest pitfall we see with substitution is taking that isolated expression and plugging it right back into the exact same equation you just started with. Guys, if you do that, you aren't actually combining the system. You'll just end up with something that's mathematically true but totally useless, like 0 equals 0. You haven't solved the thing, you've just proved that the equation is itself. So, golden rule, always substitute into the other equation. Moving right along. Section 3, Tool 2, Elimination.
Look, sometimes substitution is just way too slow, or it creates this absolute nightmare of fractions. That is exactly when we pull out elimination. Let's break down the core logic here. I want you to look really closely at the equations you're given. Ask yourself, do the coefficients for a single variable match? Like, do they have identical coefficients, say a +3 and another +3? If they do, you just subtract one entire equation from the other. But what if they have opposite coefficients, like a +3 and a -3? Well, in that case, you just add the two equations together. This is a brilliant illustration of exactly what that looks like in practice. Notice how we have a system where equation 1 has a +3x, and equation 2 also has a +3x. Because those coefficients are totally identical, we simply subtract equation 2 from equation 1. The 3x completely vanishes, and we're left with this beautiful, super simple equation where y is the only thing left to solve.
Now, let's compare that to the second example. Here, our y coefficients are a +3 and a -3. They are exact opposites. So what's our move? We add the entire equations together. +3y plus -3y is 0. They literally vanish into thin air, leaving us with just our x terms to easily calculate. It's a real game changer.
Time to step it up. Section 4, Level Up, Equation Scaling.
Let's be real for a second. Exams rarely just hand you matching coefficients for free. But look at how we can literally force the equations to do what we want. Here, we have a 3x in equation 1 and a 2x in equation 2. Obviously, they don't match. But if we multiply the entire first equation by 2 and the entire second equation by 3, look at what happens. We force both x coefficients to match perfectly at 6x. Now we can just subtract them and proceed with our elimination perfectly. We've essentially scaled the equations up to find common ground.
But you need to be incredibly careful here. The absolute classic trap when scaling is multiplying only a part of the equation. Every single term, The left side, the right side, the variables, the constants, the whole shebang must be scaled by that number. Plus, once you solve for your first variable, don't substitute it into your newly scaled massive equation. Go back and substitute it into one of the original simple equations to find your second variable. It's just so much easier.
And please, I'm begging you, do not panic if your answer turns out to be a fraction. As you move into upper-level math, numbers just don't always work out to neat, clean little integers. Sometimes y is going to equal something messy, like 13/7. The only way to know with absolute certainty if you're right isn't by second-guessing the ugly number. It's by taking that fraction, checking it in both of the original unscaled equations, and seeing if the math actually holds up. If it works in both, your fraction is spot on.
Which brings us to Section 5, Real-World Business Applications.
So, you might be wondering, why do any of these abstract x's and y's actually matter outside the classroom? Well, I want to validate all the hard work you've just put in, because simultaneous equations are not just some algebraic exercise designed to torture students. Process engineering, corporate finance, business operations, they all absolutely rely on modeling complex relationships with multiple equations. Whether it's managing inventory streams or balancing chemical formulas, you literally cannot solve multivariable reality without these exact tools.
Let's look at a real example with SoCo Enterprise. They sell mugs for $10 and shirts for $15. At the end of the day, their system says they sold 30 total items for $380 in revenue. So we've got two variables, mugs and shirts, but we also have two equations, the quantity equation and the revenue equation. The absolutely crucial takeaway here is that by using substitution, we can collapse that data and perfectly deduce that they sold exactly 14 mugs and 16 shirts. No guessing, pure mathematical deduction.
Or, consider a chemical process engineer who's working with sweet sorghum. They need a 150-liter batch of juice sitting at exactly a 16% sucrose concentration for crystallization, and they have two streams to work with, a 10% stream and a 25% stream. By setting up one equation for total volume and a second equation for sucrose mass balance, they use the exact same elimination and scaling skills we just went over to figure out exactly how many liters of stream A to mix with stream B. It is the exact same algebra, just wearing a hard hat.
So there you go. You now have the complete toolkit. You know how to define your variables, you know how to use substitution and elimination, and you know exactly how to scale equations to force a solution. You can model reality. I'm going to leave you with this final thought. Now that you know how to clear through all that noise, what complex, multivariable problems in your own life or work will you confidently reduce to a single, solvable unknown? Thanks so much for joining me on this explainer, and I will catch you next time as we keep decoding the complexities of the world around us.